moment. Alright, I'm ready.
Yes.
Alright, hello, I'm Gary Russell, and this is my presentation for my research on 3D printed filaments and ocean plastic. Now, before I get into my research, there are some terms you should first understand. When I refer to PP, that means polypropylene, GF means glass fiber, PPGF means glass fiber reinforced polypropylene, and if the term has R in front of it, that means it's recycled, and if it has V in front of it, that means it's virgin. For example, our PPGF is recycled glass fiber reinforced polypropylene. Now, let's get straight into it. So this is my research question, but this is quite hefty, so let's break it down a little bit first. So how did I get here? So when I entered this year, I had quite a wide variety of interests. Material science, I liked understanding how those works. Engineering, I liked solving problems. Sustainability was, of course, important to keep our earth clean, and 3D printing, I had some experience with that over the summer, so I kind of wanted to continue that, but I didn't really know how to unite these. So what I first did is I did a little research on all the categories, beginning with sustainability. What I initially found was that approximately 100,000 tons of plastic have been deposited in our oceans since 1950, and the majority of this being high-density polyethylene and polypropylene. And this is relevant because these materials are able to be printed by 3D printers, and this was by a study by researchers at Wellassa University. Now, moving on, I then did some research into 3D printing, and I found that the industry had many applications, whether it be the automotive or aerospace industries, and it relied heavily on plastic use. And not only this, it was only going to exponentially grow with an expected market value of $37 billion by 2026. Now, armed with this industry, which relied heavily on plastic use, and also this growing problem of plastic in our oceans, I began to develop an idea of what I might want to investigate. And that is the possibility of turning ocean plastic into 3D printer filaments that could be bought and sold as a way to alleviate or prevent ocean plastic. Now, that brings me back to my research question. So how do the properties, that's engineering and material science, that's how I'll be comparing the materials, of commercially available, well, I had to be able to get them, so that's why it's commercially available, RPP filaments from ocean plastic and or related material, that's the sustainability part, material reinforced with VGF compared with pure PPGF composites. Now you'll notice here, PPGF is not the same as PP, and that's because they aren't the same. PPGF is actually on composite, and I chose this specific strand filament because it was the only one available online that had strands available that were recycled from ocean plastic related material. Now, moving on, before I get into my literature review, there are some important properties you should understand first. Beginning with crystallinity. Crystallinity is essentially the degree of order within a material. A material that has a higher crystallinity is more ordered, as you can see from the figure on your right, and a more disordered material has a lower crystallinity, as you can see, or amorphous. Now, higher crystallinity can indicate a higher impact and tensile strength, and vice versa. Now, the impact and tensile strength, those are examples of mechanical properties, which are essentially the characteristics of a material in response to an applied force. Now, let's get into my literature review. What's been done? So I decided to conduct a literature review with two main categories, that being polypropylene and glass fiber reinforced polypropylene. And it's relevant to survey both materials, as polypropylene is a component of the material I'll be investigating, and polypropylene is also the main material that's within the ocean. I then further separated polypropylene into two categories, those that began with a recycled material and those that began with a virgin material, and then they recycled it multiple times and analyzed the properties. And I did this because I found that the studies had different results depending on the type of material they began with. Now, as for my literature review, you're going to see some stuff here. You're going to see the results, and these results have very detailed reasons on why they happened, but unfortunately due to time, I can't get too much into why they happened, so I'll only be able to tell you what happened. So beginning with virgin, a study by research Ari Kotexa et al., they found that the recycled material had a higher crystallinity, tensile strength, and an increased brittleness. And as for those that began with a virgin material, recycled material or used material, they found that it had degraded properties and an increased brittleness. And this was a study by researchers at VIT-AP University. Now, as for those that analyzed glass fiber reinforced polypropylene, they all seem to be of the consensus that it had degraded properties. And this is best examples by a study by Achuku et al. Now, after my literature review, I then determined the gap to be around the type of test, which was the fact that only a few analyzed both the tensile impact and crystallinity tests. Only a few of them seemed to do all of them, and many of them only seemed to do a few of them. And also, furthermore, none of them really investigated ocean plastic. In fact, I only found one study that actually focused on ocean plastic, which was by Pellegrini et al. And this is obvious. Filling this gap is really relevant because, of course, it's exploring the viability of a potential way to alleviate ocean plastic. And also, as there hasn't been much research done on this issue, specifically alleviating it in terms of 3D printing, it'll also serve as a guide to encourage others. Now, for my literature review, I developed a hypothesis, and this was that the recycled material had experienced degraded properties. And that's because, if you saw my literature review, those that began with recycled material found that it degraded versus those that began with a virgin material. Now, then I developed my method. And for this method, I first chose two materials, a virgin material and a recycled material. The recycled material was recycled from fishnet and rope, and although this fishnet and rope wasn't actually from the ocean itself, which may limit its applications to ocean plastic, it's still very applicable to preventing ocean plastic, which is equally as important. So then, armed with these two materials, I'd perform mechanical and material tests, and then I'd compare the properties from the data, and then using this, I'd be able to determine the viability of the recycled filaments as a solution. Now let's get into the actual methods. All right, so for these tests, they each deserve their own lecture about how they can be analyzed, so I won't be able to get into too much on how they were actually analyzed, but I'll give a brief overview on why I selected each of them and what I'm really looking at. So as we know from earlier, the impact and tensile tests, they're both indicators of changes in crystallinity. And below these, you'll see some numbers, and these are standards that are widely accepted by the mechanical engineering industry, which denote like how you actually perform the test. I chose the tensile test mainly for its prevalence in the literature and for the number of data points I could get from it that could be used to compare and gather data on how they could perform in the real world. And in this test, it's essentially the strength of dogwood specimen while it's pulled from two opposite ends, and you measure its strain, which is how far it's stretched and how much strength it's taken to make that strength. As for the impact test, this test measures the energy absorption as a pendulum is swung at an object, and I chose this test to explore a different set of mechanical properties in comparison to the tensile test, and also explore the cases where sometimes the recycled material would have a higher impact strength. Now moving on to material testing, I chose the DSC test to actually determine the percent crystallinity with a numerical value, as the other ones were only indicators. And these generate DSC curves, which you'll see left on the example, which are a little daunting to look at first, but the main things I'm really looking at is the peak crystallization temperature, melting temperature, and the enthalpy of melting, which is essentially the area of the melting peak. And the enthalpy of melting is used to actually calculate the percent crystallinity. Now for these tests, to actually prepare the specimens, for the mechanical tests, I first designed the specimens in a CAD software, and then I imported these into a 3D printer and then printed the specimens and then tested them at UML. As for the materials test, these specimens were quite small, so they didn't need to be printed. They were just cut directly from the filament and then inserted it into the machine, and then testing subsequently began. Now let's get into some results. So for DSC, the most apparent thing you'll see when looking at the graphs generated is that the melting curve for the recycled material has two peaks. And this is something usually seen in composite materials, but you wouldn't really expect this in this case, as the only expected components of PPGF are polypropylene and glass fiber. And glass fiber actually has a much higher melting temperature than polypropylene, so you wouldn't even see it on this graph. So that means there's another material present in the composite that wasn't indicated by the manufacturer. Now, if you look at their melting temperatures and compare them with other accepted values, you begin to develop an idea of what the other material could possibly be. I assumed the second peak to be polypropylene because it was similar to other values I saw in the literature. And the first peak I assumed to be high density polyethylene for a couple of reasons. Number one, at a very similar value to others that I saw in the literature. And two, we already know from earlier that high-density polyethylene is present in ocean plastic and is present in fish and rope. So it seems that was likely, if it wasn't intentional, inadequate filtering led to the addition of residual HDPE in the final product. Now moving on to the cooling cycle, it's also immediately apparent that the crystallization peak of the recycled material is much taller and wider. And this is because of interference between the two components crystallization, resulting in a larger and taller peak. Now let's get into the actual numerical values. So if we look at the percent crystallinity, which is the value on the far right, it initially appears that the virgin material has a higher crystallinity. However, if you refer back to what I said earlier, there's another material present in the composite, which means that the weight percentage of polypropylene is actually lower, which resulted in a lower calculated percent crystallinity. Furthermore, the nature of the two peaks interfering made it difficult to construct a baseline to accurately encapsulate the area to calculate the enthalpy of melting, which resulted in a lower enthalpy of melting and thus lower calculated crystallinity for the recycled material. And in light of this, it is not unlikely that the recycled material has similar, if not higher percent crystallinity when compared with the virgin material. Now, if we move over to the other values, the crystallization and melting temperature, we can see that the recycled material also is much higher in this regard. And this is likely because of a difference in material sourcing. So it may be that the recycled material is closer to a crystalline material, while the virgin material is closer to an amorphous material. And this would account for the observed differences. Now, moving on to the tensile test, if you look on the figure on the left, the figure A compares the max stress, which is sort of like the strength between the two materials, while figure B compares the strain at max stress and the strain at break. And from these figures, it can be seen that the virgin material can withstand a higher elongation or a higher strain, while the recycled material can withstand a higher stress or higher strength. And this is something quite commonly seen in crystalline materials. You see that the recycled material becomes more brittle and obtains a higher maximum stress. And this is also further exemplified by the figure on the right. We can see that there's a little plastic deformation in the specimens at the break area, which means that there's brittle fracture, and the fact that the recycled material also failed at a lower elongation means that it is also more brittle, which is something we saw earlier. Now, the other results, the Young's modulus, yield stress, and yield strain, further affirm this. The recycled material has a higher Young's modulus and a higher yield stress. The difference in yield strain was pretty much negligible, so I didn't really compare those properties between the materials. Now, moving on to the Charpy test, unfortunately, 3 of the 5 Charpy specimens didn't fully fracture during the experiment. And this meant that the actual values for those are usually considered invalid. However, the fact that they didn't fully break also means that their impact strength must have been higher because it didn't break all the way through. So in light of this, the green column should actually be a little higher. The purple column I didn't compare at all because only 2 of the specimens actually broke, which isn't enough to make any significant conclusions. Now, this is a little strange if we go back to earlier when we say that more crystalline material should have a lower impact strength. Now, the reason for this is likely because of HDPE. One particular study by Awad et al., they found that HDPE had as much as 4 times the impact resistance when compared with polypropylene. So it's likely this addition increased the impact strength of the composite. It's important to note, though, that this likely did not impact the tensile test as they have pretty similar tensile properties. All right, now let's move on to the conclusion. So from the DSC test, we know that there's likely another material present within the RPPGF composite, and also the recycled material also likely has a close to, if not higher, percent crystallinity. From the tensile test, we know that the recycled material often outperformed the virgin material in terms of strength, but was more brittle. From the Charpy test, no major conclusions were made on glass fiber reinforced polypropylene because the addition of HDPE made it challenging to know what the impact strength would have been without the addition of HDPE. And from this, we know that my initial hypothesis was incorrect. The recycled material was comparable in most cases, if not higher, in all cases. So what could the reason for this be? Well, I determined it to be likely a difference in material sourcing. It turns out that depending on where your material comes from can have quite a large effect on the properties of that material. Now, this could also mean that recycling is more dependent on the initial material rather than if it's virgin or recycled, which wasn't something I initially thought of. I thought it was more dependent on whether the material was virgin or recycled. Now, what are the limitations to this? Well, the first being the solution itself. So one of the studies I went over earlier by Achikwu et al., they found that the glass fiber actually degrades in multiple reprocessing cycles. So that means these composites can only last so long. It's only a Band-Aid solution. And also the materials used, which is something I mentioned, difference in the sourcing materials made it difficult to compare in some instances. So what are the implications of this? Ultimately, their comparability is evidence for the potential of this solution. You can actually recycle fishnet and rope and turn it into a filament, and it can exhibit similar properties. However, it's a Band-Aid for reasons I previously mentioned about it degrading after you recycle it more. Now, these limitations kind of tie into some future work. As we saw, the material sourcing kind of had a big role on my results. So a better study would be to take a single material and recycle multiple times and track its properties across multiple cycles. And this would reduce some variables in terms of sourcing. And also other forms of ocean plastic. I only focused on polypropylene here. However, there are many other types of ocean plastic that could potentially be investigated. And that's it for me.
How did you determine which results generated by your research method were most important to informing your new understanding?
Well, as I was a little new to material science when I entered this, I didn't have good enough understanding to make these conclusions on my own. So many of my results, I would first consult the literature or an expert to determine whether there was significant or played into my research. One example being the two, if I could go back, the two melting peaks. So I didn't know actually what this meant, so I consulted a lab technician at UMass Lowell, and they told me that this could be an indication of a composite, and this led me to do some research on what it could possibly be. And I found, and obviously we know this was a quite important limitation regarding how I calculated my crystallinity. So yeah, I was mostly consulting others that helped me determine what was most important for my results.
What are the real-world implications or consequences related to your findings?
Well, if I go back to what I talked about earlier, the comparability of the two materials ensures that this solution has potential. However, it's still limited because of some of the things I went over earlier about the sourcing and manufacturers. So my research indicates that there's potential in the solution, but more needs to be done on how it can be implemented. There's still many other factors. So my study implies that it is possible, and more needs to be done on whether it actually is possible.
Jared, I know you worked with somebody from UMass Lowell pretty closely here. How did that expert help facilitate your deeper understanding of the research process?
Well, first and foremost, my research wouldn't really exist without my expert, because he set up all of the days for me to come in and do my testing, so I wouldn't actually have any results without him. That'd be the first thing. But in terms of my understanding of the research process, he mainly helped me, he sort of helped guide my topic along the way. I consulted him a couple times, and the main thing he focused on during those sessions was sort of guiding me. He wouldn't really give me a concrete answer, but he encouraged me to sort of think myself on why parts of my research are important and why I wanted to pursue them. And this helped me understand the importance of developing a topic that's important to you, and also finding your own way in your topic and not having the project just given to you. And furthermore, he'd also do his best to poke at weaker points of my project in order for me to question the importance of incorporating these methods. And that's also taught me the importance of having everything in your project have a purpose, and this really facilitates a stronger question and a stronger product, because if everything has a reason and everything has importance, it all ties together really nicely. Yeah, that's it.
Brother,
Hey, Kevin!